Welcome to the Introduction to Energy Management training. In this module, we will discuss thermal energy. Thermal energy. Thermal energy can be broken down into liquids and air or vapor psychometry, solids, refrigeration, and we can look at potential opportunities. And for most of textiles, the main users of thermal energy is sanitary and drying, as well as finishing, where steam is mainly utilized in order to generate the heat required for the process. The thermal fundamentals to remember is that a change of state goes in part with energy. When we look at saturated steam, the energy content is 2,257 kilojoules per kilogram. We take advantage of changes between phases of gas, liquids, and solid states. For example, to cool a drink with ice cubes, it's solid or liquid. Cool our bodies by perspiration, liquid or gas. And cool food inside a refrigerator. In this section, we examine what happens when any of the three forms of matter is converted to either one or the other. These changes of state are often called phase changes. The formation of steam. Adding temperature to water will change the phase from liquid to vapor or gas. So, water to steam at constant pressure forms small bubbles that appear on the vessel's side, which release and float to the surface. That's dissolved gases being driven off. This is a sign of internal activity that starts to appear when water starts changing into steam. When the water becomes extremely turbulent, for example in a kettle when boiling water for coffee, steam bubbles rise to the surface and evaporate. This boiling at saturation temperature is equal to constant temperature. So let's look at the nature of steam. Steam breaking away carries little droplets of water, and that's called wet steam. It's always wet steam. It's impossible to get dry steam. There will always be water present in the system. Water droplets in suspension makes wet steam visible and cloudy. That's why we can see it. Further energy transfer is dry saturated steam, which is not visible. It has very little water content. A further energy transfer, temperature rise, gives us superheated steam, which becomes a vapor. So there's three stages of steam production. Temperature rise to saturation temperature, liquid enthalpy. Phase change into dry saturated steam, enthalpy of evaporation. And temperature rise into superheated steam, that's superheated enthalpy. Dry saturated steam is not steam which does not contain any moisture or water particular of steam, and steam without superheated state. Superheated steam is a form of steam at a temperature higher than the source liquid's boiling point, aka vaporization point, under a given pressure. It is a relative state to something called saturation or wet steam. This kind of steam is one that just exceeds the boiling point of the source at a given pressure. Here's an example of the temperature enthalpy chart, where HF is denoted as enthalpy of saturated liquid. Hg is the specific enthalpy of the saturated gas or vapor under the same listed property values. Hfg is a difference of the specific enthalpy values of the substances at the listed conditions. Of course, we should understand that the different equation is Hf is equal to Hg minus Hf. Next, we see the temperature versus enthalpy graph again. We would see there's a saturated liquid line and a saturated vapor line. We have a liquid phase and we have a liquid vapor mixture phase. If all the liquid enthalpy or sensible heat points obtained at different temperatures are joined, we get a saturated liquid line. If all the dry saturated steam points are joined by means of a smooth curve, we get a saturated vapor line. This line and the saturated liquid line enclosed in an area in which the steam is wet. To the left of the saturated liquid line state is fluid or water. To the right, to the saturated vapor line, is steam in superheated form. The wet steam area has a constant dryness line drawn in it and shown as dotted. Points along such a line have the same dryness fraction. In this example, we can see the constant dryness lines. We have our critical point, we have our superheated steam, saturated liquid, and wet steam. The saturated liquid line and the saturated vapor line, when continued up, would eventually meet at a common point called the critical point. This point occurs at a pressure of 221.2 bar and at a temperature at 374.15 degrees Celsius. It will be noticed that as the pressure increases towards a critical pressure, the enthalpy of evaporation, or the latent heat, reduces until it firmly becomes zero at a critical point. This implies that at the critical point, the water changes directly into dry saturated steam. The critical point is a division between the behavior of fluid as a vapor and as a gas. At temperature higher than the critical temperature, the vapor becomes a gas. And this slide is an example of the properties of saturated water temperature table. On the left-hand side, we have the temperatures with the corresponding values of specific volume, internal energy, and enthalpy. As can be noted that saturated liquid enthalpy is much lower than saturated vapor enthalpy, meaning there's a lot more energy being carried in vapor than in liquid. In this slide, there's properties of saturated vapor pressure table, where on the left the pressure is noted with the corresponding values of specific volume, internal energy, enthalpy, and entropy. It should be noted that the saturated temperature increases together with the pressure, meaning that the higher the pressure, the higher the boiling point or phase change temperature will be. A very important steam quality is the dryness fraction. So vapor is produced at a saturation temperature and it contains liquid droplets. That's why we call it wet vapor. Steam quality is the mass of vapor over the total mass. You can see how the dryness fraction becomes an important factor here, because the dryness fraction denotes the mass of dry saturated vapor divided by the mass of wet vapor containing dry saturated vapor. So looking at enthalpy, enthalpy is equal to enthalpy of fluid plus dryness fraction times enthalpy of the difference between fluid and gas. The steam quality of 0.98 means that there's 2% moisture in the steam. Superheated steam is used for power generation and it has no condensation of water. Remember, if your steam quality is also 0.98, the 2% moisture in the steam will eventually need to condensate somewhere. Next, we will discuss the dry bulb and wet bulb temperature. Dry bulb temperature is usually referred to as air temperature. It's the air property that most commonly used. When people refer to temperature of the air, they normally refer to dry bulb temperature. Wet bulb temperature, on the other hand, is the adiabatic saturation temperature. Wet bulb temperature can be measured by using a thermometer with a bulb wrapped in wet muslin. The adiabatic evaporation of water from the thermometer bulb and the cooling effect is indicated by a wet bulb temperature. It's always lower than the dry bulb temperature in the air. Another property to note is a dew point. It is a temperature where water vapor starts to condense out of the air, meaning the temperature at which air becomes completely saturated. Above this temperature, the moisture stays in the air. If the dew point of temperature is close to the dry air temperature, the relative humidity is high. If the dew point is well below the dry air temperature, the relative humidity is low. In this slide, we can see the dew point illustrated. The dew point here is illustrated by comparing wet bulb and dry bulb temperatures and reading the dew point temperature on your left. Thermal, air and vapor. We have absolute humidity and relative humidity. Absolute humidity is a measure of water vapor, moisture in the air, regardless of temperature. It is expressed in grams of moisture per cubic meter. The maximum absolute humidity of warm air at 30 degrees Celsius is approximately 30 grams of water vapor per meter cubed. Relative humidity is a ratio of the partial pressure of water vapor to the equilibrium vapor pressure of water at a given temperature. Relative humidity depends on temperature and the pressure of the system of interest. Next, we look at the psychometric chart, from where dry bulb temperature, wet bulb temperature, enthalpy, and specific volume can be read. The psychometric chart is especially important when it comes to HVAC or air conditioning and ventilation requirements. From this chart, we can calculate what is required in the air and what energy will be required to get the air to our desired standards. In a class exercise with the psychometric charts in the Charts and Tables book received, open up on the psychometric chart. From this psychometric chart, with a wet bulb temperature of 20 degrees and a dry bulb temperature of 25 degrees, determine the relative humidity, enthalpy, and specific volume of the air in the room. On the humidity chart, follow down the wet bulb line for a temperature of 20 degrees until it meets the dry bulb line for 25 degrees Celsius. This point of intersection lies between 60 and 70% relative humidity. That is at approximately 64%. Similarly, the enthalpy is 57 kilojoules per kilogram, and the specific volume by interpolation is approximately 0.862 meters cubed per kilogram. So the answer to the relative humidity is 63%. The enthalpy is exactly 57.23 kilojoules per kilogram. In the volume, it's 0.862 meters per kilogram.